In today's video, we're going to explore the concept of special relativity, and we will learn to describe some of its bizarre consequences, such as time dilation and length contraction. Towards the end of the video, we will look into the Lorentz Transformation, which describes the space-time coordinates of two different observers moving at relative speeds to each other. Let's introduce the concept of time dilation. What is time dilation? When the passage of time in a reference frame of a moving object slows, as the object approaches the speed of light. Now, what is a reference frame? Formally, a reference frame is a coordinate system consisting of isolated bodies all moving at the same uniform velocity. In other words, it is a point of view from which measurements are made. Let's look at a simple example. Consider two clocks. You possess one clock which is stationary with you on the Earth, whilst the other is on a high-speed rocket travelling away from you close to the speed of light. If we were to wait 10 seconds in your reference frame, the second hand on the clock will show that 10 seconds have passed. However, as an external observer watching time pass on the rocket, you will see that the seconds of the clock will tick slower relative to the seconds ticked on Earth in your reference frame. This means that the closer to the speed of light that one travels relative to a stationary observer, the slower that time passes for that observer. It's important to know that the person in the rocket does not experience a speeding up or slowing down of time. He'll experience a tick of a second as he always has done. This equation here is used to describe time dilation. Let's look at some of the variables involved. T prime is the relative time as measured by the observer, whereas T is the proper time as measured in the moving reference frame. Now, going back to our example of a rocket moving away from the Earth, if you are a person on the Earth, you are said to be the observer watching the rocket move away. So the time that elapses or passes for you as an observer is said to be T prime, whereas the proper time that passes in the rocket is said to be T. V here is the relative velocity between two reference frames, and C is defined to be the speed of light. Now, what would the time dilation equation look like on a graph? In order to do this, we need to rearrange the equation where we have T prime over T is equal to 1 over square root of 1 minus V over C squared, where T prime over T is the time dilation in fractional form. Now we can plot this time dilation against the ratio of V over C. When we do this, we notice that there is a flat region at relatively low speeds, but past 0.5, where we are moving closer to the speed of light, there is a rapid increase in time dilation. Another consequence of special relativity is length contraction. Length contraction is when a moving object's length, as seen by an observer, appears shorter than its proper length. An observer is a person in the external reference frame viewing a moving object. Appears is important because the length in the object's frame seems unchanged. Proper length is the length in the object's own reference frame. In other words, the length of the object if it was stationary. Let's look at an example where length contraction is in action. On the left, we have an observer looking at a rocket moving at a relatively low speed, whereas on the right, an observer is looking at a rocket moving close to the speed of light. As you can see in the diagram, the person on the right, the observer, will see a clear contraction in the direction of motion. What this means is the rocket shrinks in width but stays the same in height. Let's look at the equation which describes length contraction. L is the length as seen by the observer in the external frame, whereas L0 is the proper length in the object's own reference frame. This equation states that the length, as seen by the observer in the external frame, changes by a factor of square root over 1 minus V over C squared. If we were to plot the length contraction equation, we notice that L over L0 is the apparent length. Therefore, as the ratio of V over C increases, the apparent length decreases. So the closer to the speed of light an object is moving, the shorter the apparent length. Now that we've looked at two consequences of special relativity, we can introduce the Lorentz Transformation. The Lorentz Transformation is a 4x4 matrix that is used to relate the coordinates of one reference frame in terms of the coordinates in another. The Lorentz Transformation is described in the form of 4 vectors. You will be familiar with 3 vectors which describe a direction in 3-dimensional space based on the x, y, and z coordinates relative to a chosen origin. However, 3 dimensions are not enough to describe how our bodies move with time at relativistic speeds. This is because the rate that time passes is unique to each moving body. As a result, we introduce a space-time dimension. Therefore, our 4 vectors are represented by 4 columns, x, y, z, and ct.
Now, we're going to quickly derive the formula for length contraction and time dilation. Consider two ticks of your clock, TA and TB, and the moving clock, T-A and T-B. By using the inverse of the Lorentz transformation, we can find the relationship between those clocks. To do that, we simply do some matrix multiplication with which you should already be familiar with. Note that the moving clock is at the origin, so x, y, and z are equal to 0. So, we end up with delta t is equal to gamma delta t dash, where gamma is greater than unity. So, if the moving clock measures 1 second, your clock will measure a time greater than a second. For the length contraction formula, we follow a similar process. However, only y and z are 0, since we're measuring the length of a stick which is on the x-axis. We end up finding that the length observed by an external observer is actually smaller than the length observed by someone moving along with the stick.